Hello everyone. So, we will continue with the study which we are studying in that effect of fiber shape factor and fabric structure for high active sportswear, and we have seen that the almost all the high active sportswear, the fabrics are basically made of polyester filament, and polyester filaments are of different shape factors, and these are the polyester filaments used for selected for knit tennis, okay, where this different shape factors are, it is made of elliptical, hexagonal, triangular. These are scanning electron microscope images for fibers used for soccer, okay, the series S. So, similar elliptical, hexagonal, triangular, different shapes of polyester filaments are being used, and also we have seen that the fabric structure are knitted, mainly they are made of either interlock, plated or double layer structure, and these are the different characteristics. We will discuss this in the form of graphs, curve form. Now, if we see the vertical wicking in case of interlock structure, here this graph shows that time versus wicking height for different fabrics in both course wise direction, which is shown in red color loops. So, this is the course direction, and this one vertical direction is the well wise direction of interlock fabrics. So, here it has been observed that well wise wicking was found to be more than the course wise wicking of interlock structure. So, course wise when we test the vertical wicking, it is slow, which is mainly due to that course wise. If we see the liquid has to travel a longer path when it travels in the course direction in interlock structure, but well wise direction it is actually faster. Wicking height was observed more for sample having elliptical cross sectional shape of filament with the higher shape factor. So, if we see the shape factor, as we have seen, elliptical fiber has got higher shape factor than other. So, that is how it is actually elliptical fiber gives higher shape factor, and so its wicking height becomes high. Now, coming to the float plated structure, the course wise wicking was found to be same as the or a little bit higher than the well wise direction. Here the due to the structure and due to structural difference, and the well wise and course wise liquid flow is almost same. In float plated sample, the sample 4 with minimum shape factor shows with maximum shape factor. So, sample 4 if we see, it is made of say elliptical, it is with maximum shape factor shown highest wicking rate, okay, due to higher specific surface area. So, and if we talk about the two layer structure, so sample 6 S6, that soccer 6 with finer denier filament having higher wicking as compared to other. So, both the shape factor and the fiber denier here also it plays a great role in wicking. So, we can see the difference in wicking height. Okay. And if we talk about the in plane wicking, in plane wicking took place in a pattern of ellipse for interlock structure. That means that we have seen in the in case of vertical wicking, the well wise direction and course wise direction, the rate of wicking was different. The same phenomena is actually it is predominant here to have the elliptical structure in place of circular structure. So, the sample with elliptical cross section, that is the ellipse means that a water front shape is the elliptical here, and if we the sample with elliptical cross section fiber took less time because of the higher shape factor to travel same distance as compared to the hexagonal section cross section due to higher shape factor, higher surface offered. So, higher surface, if the fiber, if the pore offer higher surface, that means the drag force will be high. So, the drag force is also proportional to the surface offered by the fiber inside the pore. And in plane wicking of plated fabric and two layered fabric, here the time with the time and the water uptake, amount of water uptake. So, that it increases with the time. And coming to the absorbency. So, one is the wicking, that is a transportation, and absorbency mean it will absorb. So, absorbency capacity of all the fabric samples is high. Now, in general it is high, and saturation as compared it is completed in few seconds. So, if we see the fabrics for high active clothing has been generated, has been developed in such a fashion, it actually gives the very high wetting rate, very high rate of absorbency. Then the wicking will take place. Sample T4, that means for tennis the 4 sample was found to be the thickest among the interlock fabric. So, if we see the thickness, it is the thickest fabric, shows highest absorption. So, if we talk about the amount of liquid fluid absorption absorbed, so it depends on the thickness also, number of capillaries present. So, depending on the rate of wicking, we have to also adjust the thickness, adjust the number of capillary channel. So, so that thickness is also important to have more and more water or sweat being absorbed from the skin. For plated and 2 layer fabric, in which the sample T5 and T6 with highest porosity was found to have maximum absorbency. So, what does it mean? So, a fabric we need with a higher thickness and higher porosity, then only it will absorb more and more moisture liquid from the skin, and skin will remain dry. Then the structure of fabric, it is the duty of the structure of the fabric to transmit the moisture to either other surface or to distribute. But here the porosity, higher porosity means higher absorption, but higher porosity not necessary, it means higher wicking, because it also depends on the, if it the porosity is high with the higher capillary diameter, that means it will reduce the capillary pressure. So, that means if we have to create higher porosity, but the smaller pores. So, that we have to be very careful in designing the clothing. So, thickness is important and porosity is important for the absorbency, but for wicking our pore geometry is important. So, these are the fabrics as we have mentioned. Now, apart from this, there are different other studies available on wicking characteristics of liquid. So, in one of these it was found that the larger pore retain larger mass of liquid. Okay. But if we see the, as we have just mentioned, that if the pore size is more, so it will actually limit the advancement of the flow, liquid flow, due to higher diameter, pore diameter. As the radius of capillary decreases, the pressure generated in the capillary will be higher. So, that means we have to have large number higher porosity, but the pore diameter should be small. Okay. Increase in packing coefficient of yarn. So, if we increase the packing coefficient, means the filaments or fibers are coming closer, that means the RC, which is the pore radius of pore, will be low. So, resulting in closer fiber to fiber distance, greater number of capillary will be there, because for same yarn. So, it is a number of fiber, number of capillary will be there, and smaller diameter of capillary will be there, it will increase the capillary flow. So, that means a larger pore of smaller number and smaller pore in larger number. So, second one is better, smaller pore in larger number is better for liquid transmission through the capillary. Okay. Although the total porosity remains same, with the increase in non-roundness of fiber, which is very important. Now, a filament, suppose it is not round, it is a round, that means its shape factor is less. So, with the increase in non-roundness of the fiber, specific area increases, which causes the increase in proportion of the capillary, increase the proportion of capillary wall that drags the liquid. That is why that means the with the increased shape factor, as we have seen, that the weighting takes place due to apparent reduction in apparent weighting angle, and also in the capillary it gives a higher proportion of capillary wall, which actually enhance the drag. So, that is why the pressure increases, and this phenomena, this shows that the tortuosity of the fabric. So, if the fibers are say in angular helix cross section, helix form in the yarn, that will give, say normal yarn, it gives the wicking height, it is a lesser wicking, lower wicking height. But if the capillary channels are straight capillary channel, that will give us the very high wicking height. That means, if we increase the twist, that the capillary path will not be so it will be helix path. So, that flow of fluid will be reduced. So, that it shows that twistless yarn, in case of twistless yarn, the capillaries are straight. So, the rate of wicking is very high, wicking height is very high. Similarly, the absorbency, if we see, the absorbency is actually it is high when the pore volumes are high. Here we are not talking about the its wicking. So, here hollow yarn which has got very high pores. So, it has got very high absorbency. So, it absorbs well due to the pores, but it cannot wick. Its wicking is lesser than this, because this is lesser than the twistless yarn, because it actually due to the larger pore, it cannot create that the pressure, capillary pressure, that is why wicking height is less. With the increase in tortuosity of the pores, the wickability reduces, that we have just mentioned. It depends on the irregularity of the fiber diameter. So, as the fiber diameters are regular, so like filament yarn, the pore geometry is uniform pore geometry, but if you talk about the natural fiber like cotton, the fiber diameters are different. Even a single fiber, if we see the diameter of the fibers are different, that means pore structure developed by the cotton yarn is not uniform, and due to the random arrangement of the fiber because of the staple fiber in nature. So, pores are not continuous. So, pores are not continuous in nature, pore diameters are not uniform. So, all these things affect the transmission characteristics, wicking characteristics. Natural fibers are irregular in diameter and shape. So, the yarn produced from that, all these fibers also have irregular capillaries. So, if we talk about the fiber, natural fiber or say synthetic fiber, so or say multifilament fiber, the pore geometry, that is capillaries are totally irregular capillary in natural fibers staple yarn, and these are not continuous. This actually affect the wicking characteristics. And also for say polyester filament, if we make the texture filament and its tactile characteristics improve, its softness improves, but if we talk about the moisture in liquid form, liquid moisture transmission, it is reduced. It reduced wicking because of the discontinuity in the capillary channel, non-uniform capillary channel. So, the total capillary pressure generated will be reduced and capillary flow will be reduced. So, wicking characteristics will be reduced. So, if we compare the textured filament and normal flat filament, same filament if we use normal straight filament and non untwisted filament and textured filament, the textured filament fabric may absorb more moisture, but wicking will not be high, wicking will be slow for textured filament. So, most of the high active sportswear, high active clothing, we know that it is not the textured, it is a straight filament. And also in spinning, in staple fiber spinning, at high twist level, slow migration of fiber takes place. Okay. With the discontinuity in length, so and the orientation of capillary will be different. So, it actually it creates lower wicking rate. So, ultimately reduced wicking will be there. So, if we compare with the say polyester fiber, polyester, if we take the same polyester, one is in the filament form, another is the staple form. So, staple polyester will have much lower wicking than the filament. So, that is why fabric made of cotton or any other natural fiber have this problem. So, wicking rate will be less, although cotton has got two problems. One is that it is hydrophilic in nature, it retains the moisture, and also it actually the wicking also it is less due to the shape of the that pores. And now the in woven fabric, the wicking is affected by weave geometry and weave density. So, density of weave, that is how compact is the fabric, that means if we increase the weave density, that means yarns are close to each other, it will create some capillary pore and wicking will take place. But if the fabrics are open structure, that means it will not be able to create that pressure, the capillary pressure, the wicking will be less. So, that is why for compact type close woven fabric made of polyester filament will have higher wicking rate than open structure. And linear and steady flow of fluid through porous medium is actually governed, is described by Darcy's law. So, here Q is the flow rate, okay, flow rate of liquid, and delta p is the pressure head and L 0 is the length of the sample in that direction of flow. So, that is the this is the governing equation and K is the proportionality constant which is hydraulic conductivity of the pore. Okay. And this K hydraulic conductivity depends on the viscosity of the fluid. So, if the fluid is viscosity is high, that means the K value hydraulic conductivity will be low. That means it will create the lower flow rate of them. So, viscosity, if we can control the viscosity, we can control the K value. So, length of the sample and pressure difference, pressure is pressure head generated. So, here this pressure is generated by the capillary pressure, and liquid spreading and liquid retention. Here initially liquid spreading is achieved by small uniformly distributed and interconnected pores. That means, the liquid gets distributed within the structure. So, as soon as the liquid drop is actually it comes under contact with the fabric surface, whatever small pores, uniformly distributed pores and interconnected pores, they actually spread the liquid. Then it is retained by the larger pores. So, these smaller pores distribute the liquid to the larger pore with a high volume and they retain it. So, this is the type of the structure. If we understand this phenomena, we can control the flow. Means if we have larger pores, that means the liquid is going to stay there, remain there, because of the larger pore, means it will not be able to create the pressure. So, it will try to. So, whether do we want that type of structure or we want a smaller and uniformly distributed interconnected pore. So, if our idea is to distribute and transmit the moisture, transmit the liquid, then we need the first type of structure. If our idea is to retain the liquid, like absorbent type of weak, some wipes and all this type of application, where we need larger type of pore, where the water has to be retained there, liquid has to be retained there. So, this understanding is very important to design clothing. And now coming one very important aspect, which is called dynamic surface wetness. Okay. Surface wetness is important, okay, but what is dynamic surface wetness? Because the fabric, when it comes under contact with the sweating skin, it gets wet, that is wetness, but it has to transmit from inner side to the outer side. So, that is called, it is a dynamic surface wetness. So, under normal condition, a resting person sweats at the rate of approximately 15 gram per square meter per hour. So, this value we will see at different places. So, that it is a at different condition, okay, gram per square meter per hour. Okay. That means, if we consider the 2 square meter of our body, so 30 gram it is normally. In hot climate, it is 100 gram. So, that is the sweating rate. Perspiration rate increases with the activity level, as we know. Presence of moisture between skin and clothing creates always discomfort, even at low moisture level. So, 3 to 5% moisture if it is there. So, that also creates, it should be dry. At that level also it creates discomfort, and as we have mentioned, it reduces insulation of clothing as it becomes high, because clothing gets wet. So, that is how we have to actually there should be dynamic movement of water always. To avoid this drawback, mobility of the thin film of condensed moisture from skin to clothing layer. So, it has to move from the skin to clothing layer, the thin layer of moisture, and further to the subsequent layer. Okay. That is why dynamic surface wetness is important. So, that has to get transmitted from inner layer to outer layer, and that is through wicking. Okay. So, in cotton at high sweating condition, what happens? At high sweating condition, moisture uptake is good, that we have seen, but transfer of liquid moisture is not spontaneous due to low capillary pressure, and we have seen due to drag, formation of bond. Okay. Result poor dynamic surface wetness. So, it tries to retain the moisture. So, dynamic wetness is, surface wetness is poor, creates clammy feeling at high sweating condition. We start feeling awkward feeling, discomfort is there. But in polyester at high sweating condition, due to higher capillary pressure, if we can generate higher capillary pressure, but if we cannot generate higher wettability, it creates a discomfort. And on the other hand, for microdenier polyester or polyester with higher shape factor, presence of high number of capillaries or higher capillary wall, result high moisture uptake and dry and comfort feeling of weather. So, higher surface wetness is required, high dynamic surface wetness is required, and in shaped polyester is exactly same as that. So, understanding of pore structure, understanding of fiber structure, okay, pore structure distribution is extremely important in liquid moisture transmission, and as the wicking characteristics increases, dynamic surface wetness also increases, and this dynamic surface wetness depends on the type of pores, type of fiber, type of fabric structure. Now, we will see the different evaluation techniques of liquid moisture transmission. So, in liquid moisture transmission, and next we will discuss the moisture vapor transmission. Here in this segment we will discuss only moisture transmission through fabric in liquid form, and also in liquid form there are two stages as we have mentioned, wetting and wicking. So, we will first discuss the method of measurement of wetting, how the wetting characteristics of fabrics are measured, then we will measure the water transmission characteristics. So, wettability can be measured by, one is the tensiometry and goniometry. So, these two techniques are used for measuring the wetting characteristics of clothing. So, in tensiometry, the force tension to drag force when the fabric is wet, that is measured. So, higher drag force means higher wettability characteristics. In goniometry, the contact angle is measured, that means indirectly we can say that if the contact angle is high, then its wettability is less, or contact angle is low, wettability is high. So, goniometry it measures the contact angle in static form as well as in dynamic form. Let us see first the tensiometry. The tensiometer is an instrument used to measure the wettability of fabric by measuring the wetting force using Wilhelmli method. What is that? In this method, the wetting force the force applied by the surface when the liquid comes into contact with the surface is measured. That means, in dry condition it has got its own mass, and when it is in touch with the liquid, the liquid will try to drag the fabric. The extra force is required, that weighting force is measured. Okay? The weighting force and the contact angle here measured indirectly. If we can measure the weighting force indirectly by using certain equation, using Wilhelmli principle, we can measure the contact angle. Contact angle is calculated indirectly from the weighting force. When the solid, that means in case of, in our case it is a fabric, and this principle is used for many other material, the weighting force solid brought into contact with the test liquid using the Wilhelmli principle. Okay. Now, this is the principle. Here in this this plate, this is a plate consists of, it is a thin plate, usually in the order of few centimeter square. This is the plate. In our case it will be the fabric sample. This sample, that is plate, is often made of glass or any material where we want to measure. This plate is cleaned thoroughly and attached to the scale, okay, via thin wire. This is the scale. Now, as soon as this is in touch with the liquid, this liquid will be dragged, okay, by the plate, and there will be force exerted on the plate. The force on the plate due to weighting is measured via tensiometer or microbalance. Here with the it is measured, and it is calculated by using this formula, where the surface tension is equal to the weighting force. Okay. This is weighting force divided by the L. L is the length of contact and cos theta, theta is the contact angle. Now, this L, it is not, this is the this L is not the length of the this contact or length of the plate, it is the total contact length. In this case it is a weighted perimeter, it is not the height of the plate. Okay. The magnitude of the force on the plate instead is directly proportional to the weighted perimeter. L is nothing but weighted perimeter. Here the weighted perimeter is the length of this contact, weight length and width of the plate. Okay. So, length, width of the plate. So, 2 d is the depth and width is w. So, L is equal to 2 w plus 2 d, the total perimeter, weighted perimeter, and here we can, for complete weighting, theta equal to 0. So, from by using this formula, if we know the surface tension of a liquid against a material, if we know, then we can calculate the contact angle indirectly. So, this surface tension is actually, it's we can use some standard value. Now, goniometry principle, in this method contact angle is directly measured, okay, between the liquid and the fabric, okay, by image processing. So, using image processing by using camera, we can directly measure the contact angle, and two types of processes are there. One is static weighting angle measurement and dynamic weighting angle measurement. And in dynamic, static is simple only by using image processing. In dynamic, it depends on the spreading velocity of the contact line. So, as soon as the liquid is dropped, liquid may not remain in that same position, it as the drop, as the it will absorb the liquid, the fabric sample absorb. the contact angle changes, and that contact angle change in contact angle is recorded here. It can be measured by direct method by low power optics, okay, involve manual error, analytical method, automated contact angle tester, that is the goniometry ASTM D 572599. This method is used, or high actually that this HTHP contact angle tester is used, drop analysis tester, that is the contact angle directly. So, these are the different methods used, but the principle is goniometry principle. To observe the spreading of the droplet, high resolution CCD camera equipped with magnifying zoom lens are used. The apparatus has been developed to measure the wettability of filament specimen. So, with the filament the contact angle is measured, and the dynamic wettability, the skin dynamic wettability is also measured. It is a very important factor in determining the contact comfort feeling of the clothing. This is the equation where W is the clothing vapor resistance W, and this is the maximum rate of flow, okay, sweat flow evaporation. This is the standard, is a regularity process with the clothing, okay, and the ratio gives the clothing vapor resistance. So, that one can measure, and it is actually in ISO 7730, it is used to determine the skin temperature, sweat rate and ambient temperature for comfort. So, for comfort, if we want to measure the skin temperature, sweat rate and ambient temperature, we have to use ISO 7730, and in this method the required sweating rate, the required sweat evaporation at comfort is given as a function of metabolic heat. So, this is the required sweat rate, it is a function of metabolic heat. With this equation, m is the metabolic rate, E S W is the sweat evaporation. So, that we can use this method. Another method is that it is using the cobalt chloride, which actually sense the change in color. So, by treating the fabric with cobalt chloride, the change in color due to the absorption moisture can be observed. So, the change in color is recorded and it gives the moisture change in moisture absorbed, thereby dynamic moisture change can be measured subjectively. So, here the moisture change is measured dynamically with the, so we can record the change, we can see we can observe the change in moisture by change in color, okay. And when the fabric is treated with cobalt chloride, this is one technique of measurement, subjective measurement of moisture absorption. Now, wettability, how to express the wettability? So, wettability, the different terms are used. So, one is the bulk material absorption BMA, which is nothing but the total liquid absorption by the fabric per gram of fabric. So, in this it is a gram per gram. So, gram of liquid absorbed per gram of fabric, this is the one way of expressing the wettability characteristics. Another is the bulk absorption rate BAR, that is gram this BMA per unit time. So, that was calculated the amount of water absorbed vertically by 1 gram of fabric per unit time. So, that is a way of expression BAR. Another is bulk absorption time in second, the records the time in second it takes for water to be absorbed vertically into the fabric. So, these are the three ways of expression of wettability. In this way we can express. Now, coming to the next technique, next principle, one is wetting, next is the after wetting the next phenomena is wicking, where the liquid is transmitted. When the liquid is reached to the capillary by wetting, now pressure is generated and liquid is getting transmitted. So, transmission of liquid is, that is wicking, that is measured by different methods. Now, for wicking test, before we start to discuss the techniques of measurement, first we have to understand the liquid, which liquid we should use to have to test wicking. The normal distilled water we should not use, because the characteristics of normal water and characteristics of sweat are entirely different. Okay. So, if we get a particular result of wicking with a normal distilled water, normal tap water, it may be sometime misleading. It may give totally wrong result than in actual practice. So, that is why there is a standard liquid, standard fluid is actually prescribed, which is other than normal water. Okay. And this liquid generally used for wicking test, it should represent close to human sweat. We should actually know what is there in the sweat, then only we can try to simulate. Surface energy properties similar to the human perspiration, that the liquid which we use, its surface energy should be close to the human skin, human perspiration, heated to human skin temperature to around 35 degrees Celsius. That means, the fluid during testing has to be around 35 degrees Celsius. That means, the test which we do for wicking, it has to be performed around 35 degrees Celsius, because as the temperature changes, the characteristics of fluid changes. So, it may give wrong result. So, it should be close to human sweat, the temperature should be around the skin temperature, and sweat in the human sweat includes sodium, sodium chloride, potassium, potassium chloride, etc. So, majority is the sodium chloride and sodium. Okay. So, to simulate, so most human sweat contains an average of 100,000 milligram per liter, or at least 700 milligram per liter sodium. So, between 700 to 1000 milligram per liter, that sodium is present in our human skin. So, that is how we have to create the liquid in the fluid in that situation to simulate that is 0.25% solution may simulate this sweat. So, that is how this is the sodium chloride has an atomic mass of 58 gram per mole, with Na atom occupying 40% of the mass. So, 40% of the mass, it comes out to be that means, therefore, 1 gram of sodium per liter equals 2.5 gram of NaCl per liter. 2.5 gram of NaCl per liter, that means, if we have 2.25% sodium, so it will actually simulate to that. So, 2.5 gram of NaCl per liter if we can produce. So, NaCl is easily available. So, if we in normal distilled water, if we add 2.5 gram per liter, so this will actually closely simulate to the human sweat, and using this liquid, we can test the wicking characteristics at 35 degrees Celsius. So, in next class we will discuss the measurement of weaking characteristics. Till then, thank you.